Eva, and today I'm representing problem number 5, elastic dynamics. As the problem states, we have a rubber band which is suspended by a support. We have a metal ball on the other end of the rubber band. So after this rubber band is wound up with green turns, we get and released, we get standing waves. My goal and our goal is to investigate these standing waves, their parameters, and what affect them. So first of all, I would like to explain what we see in my experimental videos and overall experiments. So we start with after the release of the plectonym, which plectonym means that the rubber band is wind up and wind up again. So we have a loop over the loop, as you can see right over there. So after it is wind up and released, we get our first mode. However, the band is not at full length, which means we cannot take them into consideration. So further on, after it goes into a certain length, we start to see a higher mode of oscillation, and now the band is at full length. Normally, after it is at full length, we get a more stable wave. Stability is defined by the bow itself, and if there is a vertical oscillation, we do not take it as stable. So we have a transition phase. After the most stable mode, we have a transition phase to a higher mode, whereas we can see bobbing, or what I define as vertical acceleration of overall vertical motion around the axis. This bobbing is a phenomenon which occurs when there is a transition, and that is very important. So we have a rubber band which is extensible, which means after it's deflected once and the bobbing starts, it continues throughout the entirety of the experiment. What we do not get as a standing wave is this. A standing wave we define as we see all the bulges, and we just see that it is not only like the band, but also we see this. Yes, after we reach the highest mode possible, we then go to lower modes. It is not necessary to be, for example, 5, 4, 3, 2, 1. We can skip some of the modes. They skip some of the modes. So, how do we explain this? We have 4 stages. First is the storage. As I explained earlier, we have the plectonym. So this plectonym, why is wind up, it stores some kind of an energy. And after this plectonym, we define it, is after a certain number of turns which are critical. So what's the difference between this? The difference is before this end critical is reached, we get 1 energy, and after this end critical is reached and the number of winds is bigger than this end critical, we get another set of energy. And this energy is in fact, this phenomenon which occurs after the end critical is the cause for this standing wave. So after this, the loop unwinds, it kicks the band itself through inversely, which creates the start. And after the start, it goes up, then it is not repelled, rather, it is repelled, it goes up, and by the support, it is reflected back, which creates a standing wave. So, continuing on, when do these modes happen? So, first we need to explain something about the tension. We have the bow. The bow, it has much bigger mass than the band itself, which means that we can take that the tension in the band is uniform. And we can also state that the bow is very fixed and for stable modes. Now this, I do say for stable modes because we're going to see otherwise in the transitional phase what happens. So with that we can take for the standing wave as a near fixed end, and we get a discrete resonance frequency or angular velocity of the bow. So when the bow reaches this angular velocity, there is a standing wave. So it is repelled, we have interference, and the standing wave occurs. So with the angular velocity, I did take in mind that this is a theoretical graph, it is not experimental. So what we can see is 2 first one is when the band unwinds, in which we have clear modes, and when it unwinds, in which we do not see modes, if not for special cases. So here, the 4 points, which the 4 red points are in fact experimental, and we can also see that the decay from one point to the other is different, and that is because we have more energy losses. So we have in the first time where the ball is winding up and we have angular velocity which goes up, we have more modes, we also have transitions. More transition means more vertical motion, which means more energy losses. So this means that we can show the waves, and as you can see, this is when the clear standing waves occur. Now what we can notice is the difference between the highest mode and the peak of angular velocity. And that is explained because after what I explained, we have the bobbing, which is a vertical motion, and I'll talk a bit further on. So this vertical motion, as the band is extensible, we have the band itself. For example, if I have 80 centimeters, it goes into 90 centimeters, which is a big difference, and which makes the difference for angular velocity cascade, which means that the angular velocity or frequency at which we see the standing wave changes, and that means that, well, there is not going to be a standing wave at the peak, and so on. So what parameters are we going to see here? They are we have amplitude and wavelength. So how are we going to explain both of them? The first way is angular momentum. So the angular momentum of the band itself is conserved, which means that when the angular velocity, when we have a higher angular velocity, which we see the standing wave, and here a higher mode, the amplitude is going to be smaller. We can see right here, over here. Now, as we say, the points, I have taken the points from the standing wave, then just not fitted, rather the theory, and then the theory itself fits. So this is for illustration purposes. So another thing is the energy. So we have energy from the plectoning goes into wave and vertical motion. So the energy of the wave itself is defined by the number of modes and the amplitude. However, our hypothesis is not that the energy inflicts to the amplitude, but rather it affects the number of modes we're going to see. So let's see the transformation phase a bit more closely. We have a mode, but this mode starts to change, which means geometry changes, which means that there is a different needed tension, and the ball itself is a near fixed end. So it means that it starts to deflect. This is extensible. So like a spring, let's say. We can see that further on with this equation, whereas this is the motion for the ball, so ball with mass m, the big M. So we just write up the equation for motion, whereas the acceleration. So this is the graph of the bobbing, whereas we can see this is the difference between the fourth mode, then the fifth mode. As you can see, the fourth mode and overall before modes, we can see that the clearer standing waves, aka the darker dots, are all around the axis. However, when we transform to the highest mode, the most stable modes are not around the axis, they're actually at the peaks, which means that the needed tension there is in fact a needed tension for the transition. When we do a Fourier transform for this, we get that the peak as a hertz, and our goal here is to see what causes this bobbing and what is the initial cause or the strongest cause for it. So after we investigate a bit more on what is the needed tension from one mode to another, we get a 3.22 hertz for the displacement. This is my experimental setup. So we continue on with the experiments and the experimental results. So this is the graph for the highest number of modes seen. Now here the number of turns are varied and the length is fixed, so we can see that we have two parts. The first part where we have lower mode and higher modes. Now that is because there's a one more n critical threshold, which means there's two different energies for different parts of the change of n. So when we take the energy, my energy deviation, which probably we will discuss, we explain these two. Now, we're going to discuss that later, but also this is the amplitude for the number of turns per length, in which we see that the energy, the theory with the energy does not fit as well. So we take the angular velocity, angular momentum energy theory, and we see, and it's very good. It's very good fit. Now, we can see that there is a point which is not as good as the others, and that is because it starts to reach n critical, so we don't really have, we don't really have it. So for this, we kept the release energy constant, and we kept the release energy constant, and the length itself is varied. We can see the amplitude, in which we can see that the blue one is the theory of the angular momentum, and the red one is a fit. So we can see that it's pretty close.
I'm going to have to stop you there, I'm afraid.
Yeah.
So, as the opponent, if
Thank
you
you.
would like to start your first questions, please.
Yeah, could you please show us your experimental setup first?
Yeah, sure.
Yeah. Great. And so you use the step motor at the top, am I right?
Yeah. The number of counts.
Okay. Did the phenomena occur before it was like a critical number of turns, like before 200?
No, it just drops.
Not like before 200.
No.
No standing waves. Okay.
No, here standing waves, which standing Wi-Fi as an investigator.
So they were.
Yeah.
Okay. Have you provided a clear definition of standing wave in your presentation?
Yeah, I define it as a standing wave. Just we don't have like the band itself. We don't see only the band. We see also the reflection.
Can you switch to slide 18?
18.
Is it theory or is it experiment?
Theory, I said it.
It's theory.
Yeah, I said.
And angular velocity was also calculated in theory.
What?
And angular velocity is also calculated in theory.
Yeah.
Can you switch to slide 22?
Yeah.
Okay. And can you please switch to slide 24?
Sure.
So you think when angular velocity falls, the amplitude rise?
Yeah.
Okay.
This is for this is for fourth mode.
Okay, I
This
think
is
we
the
don't have to.
13.
Okay, thank you. Time's up. Please, you can rejoin your team.
Yeah.
Okay, please
My
begin.
name is Kirill Dunopoulos. I will be representing Team Hong Kong, and I will be opposing the task number 5, elastic wave dynamics. Here's the text of the task. We've already seen that, and the tasks we think that the team was supposed to accomplish were explaining the phenomena and formulation of or formation of standing waves to model the dynamics of a rubber band and investigate the properties of the waves for each parameter. So moving on to the report of to the summary of the report, the team qualitatively explained how the twisting initiates. They also explained the number of turns and how this twisting happens. They have also showed us the transitional phases and explained the bobbing of the ball. In their theoretical part, they were using a green theoretical value as the ratio of energy. The assumptions were made that the mass of the metal ball is much more higher than the mass of the string. And for angular velocity, they model from velocity cascade. They have also demonstrated us an experimental setup, but we are really unsure of its capabilities, and for analysis they have demonstrated different tendencies from parameters of number of turns, which we also consider a major improvement for this investigation. If I was to qualify the strength, first is the qualitative explanation of how is the change on number of modes, how the transitional process happening. Second one is the explain simply how the number of turns affects the number of antinodes, and the theory predicts the number of modes. But the point to improve is simply clearer qualitative explanation to the formation of modes is needed, and explain why skip some of the modes and explaining why are the modes in the first place. But we're going to touch that on our discussion. On the slide 19, only 4 experimental points were shown, which we don't consider consistent enough to show any trend. And for the slide 24, just after the release, there is 0 angular velocity. Then the angular velocity is not conserved, stored in the top of the string. So here are some points of the discussion we're going to touch a bit further. First is repeatability of the experiments, which I'm not sure about. Second is definition of the stable and unstable mode. I want to hear clear definition of the standing waves and how they're produced. Third is the shear stress and unclear quantitative theory of the motion and dynamics. And where does the theory predicts the vertical displacement? This, I think, is also very important things to discuss. For the slides, for the slides 56 and 57, there was poor theory experimental results. So I want to clearly hear the reasons for that, right? So I think we can invite that on. Okay. While you're going, I can start asking questions. So we will start with the qualitative theory. I didn't really hear.
Excuse me 1 second. Do you have a slide that you want to see?
Not for now. Later. So for qualitative theory, I didn't really hear the formulation of the standing wave. Only thing that I heard was that standing wave occurs when there is no vertical displacement. Am I right?
No. I mean,
Then can
yeah,
you
but 1 second. So, you want clear explanation of how standing wave is occurring, is that it?
Yeah.
Okay.
And what is it? Only thing that I heard in the presentation is that standing wave occurs because of the vibrations. But what are these vibrations and how are they happening?
Yeah, 1 second. I will move the slide. So, right. So what happens is after we have a loop over the loop, it starts to unwind, which.
You mentioned the vibrations that form the standing waves. Am I right? And how these vibrations happen?
Honestly, I don't really remember using vibrations. I just said that after it unwinds, it creates a displacement, and after displacement, it is then it goes to the support, wave propagation, then it's reflected, which creates the band itself.
All right.
The band itself. So it's not what I went to maybe what you want me to clarify, is that I do not take this as a standing wave. For me, this is not a standing wave, this is just a property.
Yeah, just anyway.
So what I want is after it has reached a linear angular velocity, it creates a discrete resonance. Resonance. So it forms these like approaches or whatever you want to call them. And
For a certain
this
amount
is
of time.
standing wave.
So you only quantify if it's a standing wave if it's stable for a certain amount of time.
Yeah, if it's stable for a certain amount of time, and I see it. Also, something to be defined by is the nodes. So we have points which are kept constant in the done, and that is
Okay,
the
I think that
parameters.
should have been clarified in the first place. And you also mentioned that the loop over the loop creates this displacement.
Yeah.
But do you think that only if I just twist the rubber band, store some potential energy and then release it, will there be standing waves? Yes or no? No, there will be
no
no.
standing waves.
Even then you're why? Why is that? Because there will be no vertical displacement.
Okay, let me parallel with an example. For example, I wind up the rubber band 200 times, 8 centimeters. Then I wind it up 400 times. So in fact, it does go through resonance frequencies, for example, for the first mode or the second mode. However, there will be no standing wave, simply because how the energy is transferred into the system and where it goes is going to be different. So, as I said, energy is what decides if there's going to be a standing wave, and angular momentum of the string itself decides what's going to be amplitude.
Right, but I think that your point about the energy transmission is valid, but you didn't explain it, and I didn't see any energy transmission in this system. And actually, for the formation of the waves, I actually think that even if the model doesn't reach this critical number of turns, there will still be a standing wave because of the pointing effect, which you haven't mentioned in the presentation.
Okay,
Yeah,
let's clarify, because
elongates.
that's interesting. What exactly do you think this point effect is? Because what
The
I'm
pointing
saying is about energy. It's not only about dynamics or energy, it's about dynamics and energy.
Okay, the pointing effect is when our rubber band is twisted, like when we try to stretch it out like that. Here's the cross-section area, right?
Yeah.
And the external layers actually experience more tension and more pressure on the internal layers. And since the rubber is a material that conserves its volume, it will actually increase its length, therefore causing the vertical displacement that you were explaining in your theory.
I cannot agree with that. I simply
Wait, it's just explanation of the pointing effect.
No.
Can you not agree with the
Yes,
physics?
I do not agree. Because that's your explanation of the pointing effect, that's your explanation of the phenomenon. This is my explanation. And with what I have observed at 200 turns, I do not see a standing wave. Which means, in itself, if I just twist it once, you cannot get a standing wave. You know, there's the resonance cascade, there's the energy that is going into the system.
Okay,
There's
then
overall-
maybe you should have taken more rubber bands of a different thickness, different
Yes,
height,
actually,
so you
in
could
fact,
have observed.
I did take different rubber bands. Unfortunately, I couldn't include my presentation, but I did, with which are more not stiff, but rather.
And still, there was no phenomena until 200 turns.
Yes, I mean the critical value did drop, but yes, after the critical, I did not see it.
And actually,
I did not.
as I see from our conversation, you're stating that the phenomena only occurs because of the resonance.
No. I'm saying it occurs when there is the resonance.
Yeah, so
It
it's
occurs because the energy is going into the system. But so what I want to explain in my presentation, and actually for it, so it's easier to follow, as first I start with how it starts, then when it starts, then about what exactly
Okay.
a standing waves.
Yeah, definitely. You have described that, but I wanted to see the energy motion because I think it's the most crucial part of this system. I can explain that. I
Okay,
can see
yeah.
so you can see my vision of it, right?
Yeah.
So when we twist the rubber band, it
Yeah.
acts as a pendulum, right? So
Yeah.
there are like torsional waves created.
Yeah.
This creates
There's no torsional effect. It's torsional pendulum. When you twist it a little down, it's torsional pendulum.
Yeah,
But
yeah,
in definition for this problem,
Wait a
you need
second.
many times to twist it.
yeah, many times.
Yeah.
What you expect is many times. I've only turned it for like 20 turns, and it was enough for the any wave to
What was
occur.
your length? What was the length that you used? Because that's really
60
important.
centimeters. From 20 to 100 centimeters, I varied everything. So,
60
wait, you
centimeters.
didn't allow me to actually
Look.
tell my definition of it. Wait, can we actually talk about theory then?
Yeah.
Because if you,
Yes.
because on qualitative part, I just don't really agree with your definition of the process. Theoretical, yeah, like 15 and 16.
Yes.
Wait, can you, 20?
You said 26.
Wait, 20.
20.
Yeah.
Okay.
Yeah. Do you think 4 dots are enough for us to make this assumption?
I really like that you asked these questions. So it is not about if I try to measure several different times. I tried with the bigger ball, have the ball straight in line, and I tried with the disc, and then the ball, and
Wait. If you tried it many times, where are the error bars?
no. Here's the thing. When I tried different times, my camera simply cannot get the angular motion.
Then how do you get these values?
So I got 4 values. So what I did was, with the 96 FPS, we have 1 second of motion. We can actually get photo of.
So is it tracker? What was it tracked just by video?
Yeah, the angular velocity was tracked by video, and because the
Wait,
ball
it
is
still
small,
didn't explain me why there are no error bars.
because look, there are no error bars because I have not put them. But
Oh,
that
okay,
does not mean I
okay,
can
that explains.
the experiment, and
Wait.
moreover, they
Then
have
how
4
did you
points because that's all
how
I
did
could
you
get
measure
with
the
everything.
velocity then? Yeah, definitely. Yeah, like for measuring the angular velocity, you don't see the points when they like rotate at a certain position. Then how did you measure the angular velocity, judging from only one position of the camera?
No, I got 2 positions on the camera. I got 2 cameras.
Two cameras?
Yeah.
Oh, okay, that
One
explains
from
it.
the
Right.
side, one below it, taking photos of
you.
taking
Thank
a
you.
video
That's right.
of the phenomenon.
Then I want to see slide 24.
Okay.
Then it aligns with your theory, right?
Yes.
As an angular velocity falls, the amplitude rises. How is that?
Alright. So I do want. I would like for everyone to notice that this is angular velocity of the mode that appears. So we have angular velocity first, which then appears the first mode.
Wait, but then
the
you
second
think
mode.
the angular velocity
So-
for all the points of the rubber band are the same?
And yes, the ball causes it, and I'm investigating the motion of the ball. Now, the ball type.
I would say that they're not the same
angular
since the
velocity.
radius is here is a bit different from the radius here. This point is here, you know.
No.
So the angular velocity, I would not say that it's uniform for all the experiments. So I do not
May
agree on that.
I just state what I did in my experience before you judge them?
Alright.
So when I say angular velocity, I search for the angular velocity of the ball itself. Then
Also,
when I
for the-
say
sorry, you
angular
just said that
momentum,
it was for
can I just finish? Thank you.
right.
So when I say angular momentum, I mean angular momentum of both the ball and the band. Angular momentum of the band is different from the angular momentum of the ball. So yes, I did take in consideration that here is 0 and here there is a.
Then why did you take it as a
Okay,
unit?
thank you very much.
Right, thank you.
Get out a summary, please.
Yep. So I think after the conversation with the presenter, I understand more their vision of the task and how did they, what was their approach to it. However, I do not agree on the phenomena explanation itself, on the qualitative analysis, which I think is the basis of the whole experiment. And I also had some question about the theoretical line, the dots that they have acquired, and the setup, which I consider the major part, the crucial part of this task. The qualitative, the base, and the setup, the analysis. So I do not think that the team has provided a clear and full, that they have fulfilled the task in in depth. Maybe it's just very shallow analysis. So yeah, I wish the reporter would investigate in such parameters more time. And yeah, thank you.
Thank you.
Which material properties such as elasticity were determined how?
Excuse me, I can't hear you. 1 moment.
Which material properties such as elasticity were determined and how?
Right, so they were done first. So I have the cross section of the string itself. Then I put weights, different weights, and see the strength of
So
it.
experimentally.
Yeah.
Okay. How does your release mechanism actually work?
So what I have is it's the experimentation that I showed. It winds up. Then I make sure with the stative with.
Do you wind it up by hand or the step or what?
No. I have the motor shown.
And then you release it by hand.
No. I have like a sztywka, like a clip. I have a clip. Then after I'm sure that it's
Yeah, okay.
vertical, I
Yeah,
release.
okay. And in your model, how you said you modeled horizontal motion? How? It wasn't clear how you modeled the horizontal
Horizontal
motion.
motion. What do you mean horizontal motion?
Like, yeah, it doesn't matter. How do you excite the different modes and the waves?
They are excited when the resonance cascade or angular velocity of the bow goes through this range of the resonance or the discrete angular frequency at which that bow
Okay.
excite and influences
opponent,
aligned.
do you think the pointing effect is relevant for the wave formation?
Yeah, I think the pointing effect actually plays the crucial part. Or if my answer is right, if I think I can elaborate. I think it plays a crucial part since it transforms this motion of rotation into a motion of vertical displacement, which then helps us to create the actual standing wave that we see.
Porter, what do you think of that? Do you agree or?
That's his theory. That's what he has researched. I have researched other, and my experiments align with what I presented just now.
Okay. Can you predict the amplitude?
Yeah, I can predict it with angular momentum and overall. That I take, I first take the amplitude for the steady, and I take the amplitude for the measure. Then I have that using all the conditions as near fixed, and I get an actual amplitude.
You said that modes can be skipped. How does that work? How do you think that works?
So we have energy. The modes are which modes appear is defined by energy. So after the released energy transforms into the system, it can energy is dissipated not only in the wave but also in the bobbing, which means that if it does not have the energy for this mode, it skips.
Yeah, okay. What do you think? Do you agree?
Sorry, could you quickly?
I'm afraid you're out of time. Thank you.
We've already heard the problem statements, I'll skip over it. So, beginning with the reporter, we think that it is good that the transition phase and bobbing were investigated, and that it was done well, and that the camperdown, well, I can't pronounce it, you know me, that they were considered a model, we find that good, and the dynamical model for the metal ball and that horizontal motion and stuff were considered, we find that very good, and that the third investigation of the bobbing is a key point, and that is very good that it was investigated. Some parameters were investigated, and including the length and length and stuff. But it wasn't clear how the model for excitation works, and that the theory doesn't really match the experiments qualitatively. We find that bits of optimum that should have been discussed more, and that the little quantitative predictions were suboptimal in this, and that time management was generally poor, especially seeing as they skipped over slides, the presentation they didn't manage to finish, and in total it was hard to understand and follow along due to that. The experimental setup was not explained very well, but this was later clarified by the opponent, and in turn we think it was good, but it wasn't explained in the main presentation. The inconsistent release mechanisms we found not really acceptable, and that the lack of error analysis really is a detriment here, and that the material properties weren't really explained in the presentation, how they were measured, but we later clarified this, and we considered okay. We asked the opponent then asked about the experimental setup, which we found very good, and he did manage to clarify it a bit. But he did point out the lack of thorough explanation of mode formation. This later was also clarified a bit. And the lack of experimental data points was also very exquisitely talked about. And he also asked about the theoretical model and asked good questions to it. And he clarified the usage of 2 cameras, which was still a bit unclear in our opinion. However, the prioritization of questions could have been improved drastically, as they weren't very clear and they sometimes also sounded a bit aggressive. He also mostly talked about the phenomenon, for instance, pointing, rather than actually what was done in the report and trying to improve it. He mostly brought in his own opinion, which we feel could have been improved. The prioritization in the discussion was also really not ideal. He could have done a much better job at that. And he also rarely talked about his own opinion, only brought the reporter down, which we didn't find very fair or nice. And he barely talked about the mismatches in the comparison of the theory and the model. And the discussion really didn't help us understand the point of the report. He only brought in his own opinion, which is not what the opponents meant to do in our opinion. Now, coming to discussion analysis, we began with how standing waves are actually formed. That's what the opponent asked. And the reporter then said that it creates horizontal displacement depending on the resonance. And it was discussed a lot, and a lot of time was spent on it, but we still didn't really completely understand how the waves are actually formed, and how higher modes in particular are formed. It was never really made clear to us. Now, afterwards, the pointing effect was discussed, and the opponent said that the pointing effect takes place. The reporter said it was relevant, but not that important. And we agree with the opponent that the pointing effect does take place, but it wasn't really as relevant for the formation as it was made out to be. And he shouldn't have spent as much time on it and maybe prioritized other things, as it was also mostly his own opinion, and again, he didn't really try and improve the presentation. So again, just his own opinion was irrelevant, as we don't consider it as relevant to the presentation. The error bars were also pointed out by the opponent that they are missing, and the reporter claimed that they were not plotted, which we didn't completely understand. I think we may have missed over that. But we do agree that the error bars are missing, and it's a really important thing, and that it should have been talked about way more in the discussion, and also been brought to explanation by the reporter in the actual report why. Afterwards, video tracking was talked about, and they talked about how angular velocity was measured. The reporter claimed 2 cameras were used, with 96 FPS apparently, which we also wanted to touch on, but we didn't have enough time in the questions, as we don't consider that sufficient if it's only 690 FPS for both cameras, as it could be improved upon for such fast movements. It should be a higher FPS. And this was also not really explicitly stated in the report that there were 2 cameras, and but it was good that it was clarified in the discussion by the opponent. Then, the relation of angular frequency was discussed, and the opponent asked how does the relocation of the angular frequency and the amplitude arise. The report then talked about that the angular frequency is that of the metal ball. And we agreed with the opponent in the sense that after the explanation, it did make a bit more sense, but it wasn't completely clear. And again, as for the last few things, it should have been talked about more in the actual report. But all in all, the reporter did do a good job, but the opponent did not act very fair. Thank you.
Okay, final summary. You can start straight away.
Okay. First, I want to thank both the opponent and the reviewer for the points taken. However, I do want to state that in my report, I explained how the standing wave starts, when is it actually, and what exactly am I measuring in the standing wave, what are in the stable standing wave, what is important. So I would just want to clarify that when we have the angular velocity of cascade of the bow itself, so this means it goes through ranges of these modes that could be excited, and I'm saying could because that is decided by the energy, and if the energy is enough at that point, if there is no additional bobbing, if the tension is right, there is a standing wave. So about my experimental setup, I will take the points taken. However, for the measurement of angular velocity, we had, I'm sorry for, I misspoke, but I have 960 FPS below and 240 for the standing wave itself. That was minor, I apologize for it. As well as for the error bars, I have done several measurements, and I want to touch a bit on the reproducibility of this phenomenon. And it is in fact really not so reproducible because it really is defined by not only by the release mechanism and the initial conditions, which are pretty hard to achieve a perfect setting, as well as this problem has many aspects in it, such as the dynamics and the energy, which means that the indiscrepancy between the theory and the experiment is in fact a normal thing for such a hard problem, in my opinion.
Okay, thank you very much. Can I have all three of you stay at the front, please?
Yeah, I'm taking my
Well, you might need it. Okay, so if we are ready, Patrick, can you start us off?
So, can you put up the slide, please? Yeah.
Can you
The
put
slide.
your complete picture?
Yeah. So on slide 19 and 20, you say you have the theory, right? And yeah, let's wait until you put the slide on it.
Okay, so while
If
we're
someone
waiting,
has a
can I
question.
ask the opponent, can you just confirm the range of parameters that were actually tested in the experiment, please?
The actual parameters that were tested in the experiments.
Yeah.
I think they varied the length, they varied the number of twists, and we have also seen that they have recorded the amplitudes depending on the number of twists also. Yeah, I think the number of twists and the length were the main part that they have concentrated on.
Okay, thank you. Yeah.
So on this slide and then also on slide 19, you have this curve which you say is the theory.
Yeah.
Can you show where is the equation that describes this?
Right, in my presentation I don't have it, but it's just harmonic damping, and for the first one I have one coefficient, and for the second half I have another coefficient.
Can I answer?
Yep, Alex.
So I assume you investigated what happens when you twist for a certain number of times, yeah?
Yeah,
What is the range of
my experiment.
twists? Like you started from
Oh, yeah.
200, from 20 up to what number?
Yeah. So for example, this is my graph for the number of modes of second order and the number of twists. So I start from 200 up until 800.
So does your theory predict the number of, the number of antinodes depending on the number of turns?
Yeah, the maximum I could get. And yes, when I did several experiments for every point. And yes, again, I say this is not a reproducible, not really reproducible experiment. So sometimes I get different maximum modes. I take this, which are the most common ones.
So
And
it's not repeatable, yeah?
Yeah, I mean, we can see, sometimes we can see the same number of maximum nodes, sometimes we do not see just the
Okay,
same.
thank you. On this graph, for
Yeah.
example, you've chosen to plot k max squared.
Yeah.
Why did you choose k max squared rather than not just k max or?
So what I take in this model is I take the energy of the wave and then I take the released energy and I say fraction of the released energy goes into the standing wave. And for the standing wave, we
So
have
why
kind of
choose
second order.
k max squared?
Yeah, because of the energy in the standing wave is of the
So
second
is there
order.
an equation that
Yeah.
predicts that you're using?
I have on a hidden slide, but yeah, this is for the wave. This is the equation for the wave, and I take that fraction of the previous equation for the storm
So
energy.
there was some reason for it. Thank you.
Yeah.
Patrick? No, no.
Can you go to slide number 18?
18, okay.
Is this 3D or experiment?
Yeah.
Can you show me the equation which generates this graph?
Yeah, I don't have it in the presentation itself, but the first half in which I said is just a damped harmonic oscillation with a certain coefficient, and the second is just with another coefficient.
But then why is there abrupt changes at 1, 2, and all these points? Shifts. Like it's not a
The derivative changes.
Yeah.
The rate of what?
The slope changes.
yeah, it's not a,
You see, like at point 1, the slope suddenly changes.
at 2 and 3 and
Yeah, I'm changing the coefficient. I'm basing that into plot. Maybe something like that, or just I just.
This was just drawn by hand or?
No, it wasn't drawn by hand. It was in Excel. Yeah,
Okay.
because there are different coefficients in
Alright. You also said the angular velocity of the system remains constant.
angular momentum.
Angular momentum, okay, remains constant.
Yeah.
So
In yeah.
before you release the ball, what's the angular momentum of the system?
Before I release it.
Yeah.
It's true.
So when you release it,
I'm saying that in the stable modes when we have a mode, angular momentum is
so
one
only
thing.
within
angular-
the stable mode.
Yeah. That's why I my equations I have omega k on it.
That's fine.
On top.
Okay, thank you, judges. Our time is up. Well done, everyone.